Hello, I am Srikar Babu. As a part of the RIS 2024 program, I worked with Srijan Deolasi, Woojan Kim, and Professor Katya Sikara associated with the ART lab. My project is titled Offline Reinforcement Learning for Informative Path Planning. Let us start with understanding what informative path planning is. Informative path planning, or in short, the IPP problem, aims to design a path that maximizes information within a resource constraint in a given environment. Formally, we want to find an optimal trajectory psi star that maximizes information gain, represented as I of psi within a budget denoted by B. The applications of IPP are widely varied. To name a few, IPP solvers are used for search and rescue tasks, wildfire exploration, and precision agriculture. Prior work in IPP can be broadly classified into two types: traditional methods and learning based methods. Traditional methods or non learning based methods often rely on optimization techniques. Traditional IPP solvers include graph based approaches, receding horizon approaches, and sampling based approaches. Limitations of these techniques: they're often computationally intensive, they require a lot of time for each planning step, and struggle with handling large search spaces. Moving to learning based methods, these methods usually rely on reinforcement learning. They allow the agent to plan adaptively while reducing the computation cost and ensure faster planning time. But for utilizing reinforcement learning, we need to train a policy, and this requires extensive environmental interactions. This raises safety concerns and could be cost intensive when training to deploy in a real world environment. Our solution to these problems is to employ offline reinforcement learning. Offline reinforcement learning leverages pre-collected dataset to train a policy. We can learn optimal or near optimal policies without any real-time environmental interactions. We also note that offline RL does not require the dataset to contain optimal trajectories. Even with suboptimally performing trajectories, offline RL allows to train a policy to achieve satisfactory performance. Note that pi beta here is termed as behavioral policy, which could be any arbitrary method or heuristic used to collect the dataset, on which we train an offline policy that is referred to as pi. Let us take a step back and ask the question, why offline RL when training with a dataset? Turns out there are some challenges when training a policy from a dataset. This is commonly referred to as extrapolation error that arises due to distributional shift. In detail, the values estimated while training, such as Q or V values, are poorly represented. The reason why this happens can be accounted to one of the following: absent data. The absence of some state action pairs in the dataset leads to poor representation of these values. Model bias. This arises due to bias samples in the dataset that hinder the Bellman operator used to update the value functions. Training mismatch. This arises due to misalignment in the distribution of the data with the actions recommended by the current policy. The solution to this problem is to use offline reinforcement learning, among which we use an algorithm known as batch constrained Q learning. How does batch constrained Q learning work? The algorithm suggests that we estimate behavioral policy pi beta used to collect the dataset and ensure that our policy pi, parameterized over theta, to be close to the behavioral policy. The objective of this algorithm is to minimize the distance between the selected actions and the actions in the dataset, and also lead to states that are familiar or present in the dataset, while also maximizing value function to reach optimality. The behavioral policy is learned using negative log likelihood function, and the Q value is learned using a modified temporal difference update, which constrains the action to be close to the behavioral policy. Also, extracting the policy out from the Q values, we again ensure that the policy does not deviate very much from the behavioral policy, while also ensuring we choose the best possible action. To incorporate the idea of offline reinforcement learning to informative path planning, we propose the following pipeline. We use Gaussian processes to model the agent's belief. Gaussian processes allow interpolation between discrete measurements and interest map, allowing an approximate representation of the ground truth. We use probabilistic roadmap graph to discretize the state space. The state in our formulation includes the agent's location in the environment, agent's current belief, leftover budget, and executed trajectory so far. The action taken by the agent indicates the next node to travel to in the probabilistic roadmap graph. We use an encoder decoder style architecture using attention mechanism inspired from the catnip model, which is an IPP solver that uses reinforcement learning to ensure that the agent is spatially aware. We evaluate our model's performance in a 2D environment that includes randomly generated Gaussian distributions within a unit square to model the interest. In order to compare various methods, we consider the trace of the covariance matrix of the Gaussian process. This indicates the uncertainty present in the agent's belief. This translates to a lower covariance trace, indicating better performance of any method. To train offline RL policy, we consider four datasets, each consisting 18,500 episodes or trajectories. Expert dataset. This dataset comprises of optimal or near optimal trajectories that is obtained by deploying catnip's fully trained policy. Medium dataset. This dataset comprises of trajectories collected by deploying partially trained catnip's policy. Medium expert dataset. This comprises set of trajectories that is a combination of expert and medium datasets. And finally, greedy planning dataset. This is obtained by deploying a non-learning technique that relies greedily acting based on entropy of the on based on the current agent's belief. We compare our method's performance with traditional methods such as greedy planning and RAOR, which stands for randomized anytime orienting. We also compare our approach's performance with behavioral cloning or BC that tries to imitate the behavioral policy used to collect the dataset. We observe that our method is able to outperform traditional approaches as well as behavioral cloning techniques, while also ensuring that planning time is reasonable. We demonstrate the qualitative performance of our model for one of the instances with a budget of 10 in the figure. In order to show the real world applicability of our method, we deploy our offline train policy on the expert dataset on a Kepra 4 robot. We mount a Raspberry Pi with a camera module on top of the robot to capture observations from the environment. Here is the robot in action. In conclusion, we propose a method to learn a policy for informative path planning without environmental interactions. We use offline reinforcement learning, specifically batch constrained Q learning, for training our policy. We adopt an architecture inspired by catnip to ensure spatially aware decision making. We show that we are able to achieve satisfactory performance even when the policy is trained on suboptimal trajectories. Future work includes extending this to a multi agent setting where multiple robots explore the environment. Also, this work can be extended to spatiotemporal environments. Thank you. I would like to take this opportunity to thank Srujan, Bhujan, and Professor Katia for guiding me through this project. I would also like to thank the RIS organizers, Professor John Dolan, Mrs. Rachel Birkin, and Miss Morgan Grimm for this amazing opportunity. Thank you.